Good morning, everyone. My name is Calvin Wu, along with my fellow colleagues Alexandra and Harizal Lim. Today, we will be presenting our research titled A Curated Multi-Source Borrow Dataset and Benchmark for 3D Single-View 3D Reconstruction Models. This work looks at how modern single-view 3D reconstruction models perform when we evaluate them on one specific object category, which is bottles. The main idea is simple. Current benchmarks often report average performance across many object categories, but if we only look at the average score, we may miss on how a model behaves on one practical object type. Next. The problem is that aggregate benchmarks can hide category-specific behavior. A model may perform well across many object classes on average, but that does not always mean that it performs well for specific object categories such as bottles. So, in this work, we focus on one question. What happens when we evaluate modern reconstruction models only on bottles using a controlled benchmark? Next. Most modern single-view 3D reconstruction models are evaluated using multi-category benchmarks. Bottles may appear in these datasets, but their performance is usually not reported separately. This makes it difficult to know whether a model can reconstruct bottles well, and also what kind of bottle shapes are harder to reconstruct. This is the gap that our paper tries to address. Next. The objective is to benchmark single-view 3D reconstruction on one controlled object category. Our first contribution is a curated multi-source bottle dataset. The models are collected from ShapeNet, Thingiverse, Objaverse, and Sketchfab. Our second contribution is a benchmark of three models: OpenLRM, PixelNerf, and SplatterImage. Our third contribution is a more detailed analysis. We report both overall performance and performance across the 5 bottle shape groups: contoured, straight, bulb, tapered, and other.
These slides show the overall pipeline. First, we collect bottle from 4 different 3D asset sources. Second, we pre-process and standardize the dataset. These include format conversion, category verification, duplicate removal, splitting files with multiple objects, post and scale normalization, quality control, and shape classification. Third, we fine-tune and evaluate the 3 reconstruction models. Finally, each model receives the same single rendered image as input. The reconstruction 3D output is then compared with the standardized ground truth bottle mesh. Next. For the evaluation, we use 3 metrics. First, the IOU measured global volume overlap between the prediction and the ground truth. The higher is better. Second, chamfer L1 distance measure how close the predicted surface is to the ground truth surface. The lower is better. Third, normal consistency measures whether the surface orientation is aligned with the ground truth. The higher is better. We use these 3 metrics because the reconstruction quality is not one-dimensional. A model can capture a rough shape well, but still have weak surface detail. Another model can have better surface alignment, but weaker global volume. Next. For this aggregate result, the model is ranking depending on the metrics. OpenLRM achieved the best IOU, meaning it performed best for global shape overlap. SplatterImage achieved the best chamfer L1 distance and normal consistency, meaning it performed better for surface proximity and surface orientation. PixelNerf performed weaker overall under this controlled bottle benchmark. So, the result is not simply that one model is always better. The stronger model depends on what aspect on reconstruction quality we care about.
All right, for the subgroup results show another important point. Reconstruction performance change across bottle shapes, regular bottle structures, such as straight, taper, and contour bottles, generally produce stronger reconstruction scores. And then the irregular, the other category, is the most difficult. These models have less standard geometry, so the models struggle more to reconstruct their shape accurately. This shows why subgroup analysis matters. If we only report aggregate results, we miss the weakness that appear in the specific model structures. And then from these results, we interpret OpenLRM as stronger for coarse volumetric reconstruction because it gives the best global overlap. Splatter image is stronger for surface level reconstruction because it gives better surface proximity and orientation alignment. So, and for the pixel nerve performs weaker compared with the other two models in this benchmark. There are also limitations. The study only focused on the models. The image are rendered under a standardized setup, not a real-world image conditions. Also, public 3D assets may still contain mesh defects even after pre-processing. Finally, the metrics evaluate geometry, not texture or material quality. And for the future work, this benchmark can be extended to similar object categories such as faces, mugs, and bowls. To conclude, category-specific benchmarking gives a model transparent evaluation of model behavior. This work contributes a curated multi-source model dataset, a control benchmark of 3 reconstruction models, and an analysis across different model shape groups. The main takeaway is that bottle reconstruction difficult depends on structure. Irregular bottles reveal weaknesses that are hidden by aggregate multi-category benchmark. So instead of only asking which model has the best average score, we should also ask which kind of object structures each model can reconstruct well. And then that concludes our presentation. Thank you for listening. I'll be happy to answer any questions.